Hello everyone, my name is Shudipto, and on behalf of my team I am excited to present our project Flood Probability Prediction using machine learning and deep learning. So flood, as we all know, is a major problem worldwide. It causes significant loss of life and property. Thus, accurate and timely prediction of flood is very important to save lives and properties. Our paper mainly does a comparative study of various machine learning and a deep learning model. It has been performed on a dataset of 50,000 instances with 20 features related to meteorological, hydrological, and geographical factors. So, first you may ask, how are floods predicted normally? Floods are normally predicted through hydrological and hydraulic models. While they are robust models, but they are very data intensive, they are computationally expensive, the data is rather hard to find, and the computation is, as I said, very expensive. So, what we have done, we have compared various machine learning and deep learning models like random forest gradient boosting, XGBoost, AdaBoost, K nearest neighbors, and convolutional neural networks. And we have also implemented a deep learning algorithm, that is multi-layer perceptron. These will help us achieve more accurate results than conventional models like hydrological and hydraulic models, while being faster, as they are taking much less time to compute the predictions. Moving forward, we have included a literature review which covers various articles and journal proceedings based on flood prediction using machine learning and deep learning models. The report also covers how we have processed the dataset, how we have cleaned and created relation among the various features, and then processed the data using exploratory data analysis, and then we have trained our models. Then we mainly evaluated our models based on some factors like mean absolute error, accuracy, precision, recall, F1 score, AUC, and ROC. And the results are discussed in this paper. Now, if we have a brief look at the code section, all of the models were provided to us from scikit-learn library. We have used the scikit-learn metrics, and we have used NumPy and pandas for data processing, data analysis, and we have plotted the data using matplotlib, and we have used Seaborn for the statistical graphs. Now, it brings us to the core problem we aim to tackle. For years, we have relied on traditional flood forecasting methods. While valuable, these hydrological models often have limitations, as we have already discussed. Uh, Thus, our goal was to address the gap and do mainly a comparative analysis on the models we have trained. And these models are used to predict the probability of flood in a region based on the factors. So that's all from my side. Thank you all.
Hello everyone. In this part of the presentation, I am going to describe the how it is done part of our project. This is the exact steps that we took to build and test our machine learning model for the flood prediction. Our goal was to find the most effective and accurate method for predicting flood probability. Our methodology can be broken down into four main parts: understanding our task, pre-processing the data, building the model, and finally evaluating them. Let's first talk about the dataset. We started with a solid foundation, a large dataset specifically designed for the flood prediction. This dataset contained 50,000 samples with 21 different features. The features were not random, they covered a wide range of factors that are known to influence the flooding. We had different kinds of features, like some of them covered environmental and geographical factors like monsoon intensity, topography, drainage, deforestation, and climate change. On the other hand, we have also features like human activity and infrastructure, such as urbanization, the quality of dams, agricultural practices, and the effectiveness of disaster preparedness. The main goal was to predict the target variable, which is the flood probability. A continuous value was showing the chance of flood happening or not. Most importantly, the data was clean with no missing values, which gave us a great starting point. Before we begin to build our models, we looked at some previous research related to our topics. We found that while many studies have been done on this topic, but there is still need for more research focused on specific regions with unique characteristics. Our study aims to contribute to this by applying and comparing a range of models on a dataset that represents such areas. Let's talk about the data preprocessing. With our data and the background research ready, the next step was data preprocessing. This is a crucial step to make sure that our models can perform at their best. We did this in three steps. First, we explored exploratory data analysis called EDA to understand the dataset better. We looked at how the data was distributed and checked for correlations between the features using the correlation matrix. This helped us to see if any features were strongly related to each other or not. Next, we scaled our features using standard scaler. This process normalizes the data, which is very important for certain algorithms like KNN and for helping neural networks to train more efficiently. Finally, we perform train test split. We split our dataset into a training set and a testing set with a ratio of 75 by 25. We used the training dataset to teach our models and the testing dataset to see how well they perform on new or unseen data. Let's talk about the machine learning and deep learning models that we have used in this project. Once the data was preprocessed, we trained several different models to see which one would perform the best. We used a mix of traditional machine learning models and one deep learning model here. For machine learning, we used well-known ensemble models like random forest, gradient boosting, XG boosting, and AdaBoost. We also used k-nearest neighbors, which is a distance-based machine learning algorithm. For deep learning, we implemented a convolutional neural network for which our tabular data worked like a multi-layer perceptron. This model has three hidden layers and used a modern technique like Adam optimizer and early stopping to prevent it from overfitting the data. Lastly, let's explore how we measured success of our machine learning model. Obviously, we have used evaluation metrics. To know which model was the best, we needed a fair way to measure their performance. We used a comprehensive set of matrices for both regression and classification tasks. To measure how accurately the model could predict the exact probability of a flood, we used the regression metric mean absolute error. To measure how well the models could classify an event as a flood or non-flood, we used metrics like accuracy, precision, recall, F1 score, and AUC. This structured approach allowed us to systematically build our models, train and test them, and then rigorously compare their performance to find the most reliable predictor. Now, let's move on to the result and see what we have discovered.
Now I will explain the result of our study. We evaluated six models: random forex, XGBoost, gradient boosting, AdaBoost, KNN, and CNN. Their performance was compared using three key matrices: accuracy, F1 score, and AUC. From the result table and the graph, it is clear that the CNN model achieved the highest performance. It reached an accuracy of 99.99%, F1 score of 0.98, and AUC of 0.99. This indicates near perfect classification ability, making it the most reliable model for flood probability prediction. Among the traditional machine learning model, XGBoost was the best performer with an accuracy of 86.71%, F1 score of 0.91, and AUC of 0.96. This shows that XGBoost was able to handle complex data pattern, but it still could not match the deep learning model. Gradient boosting also showed good performance with almost 80% accuracy, F1 score of 0.9, and AUC of 0.97, proving its consistency as an ensemble method. On the weaker side, random forest, AdaBoost, and KNN did not perform as well. Random forest had the lowest accuracy of 56.72%, though its F1 score was moderate 0.86. AdaBoost and KNN both reached about 66% accuracy with AUC values around 0.93, showing they had limited predictive strength compared to boosting method and CNN. Additionally, when we look at the ROC curves, give us a very clear visual comparison. The CNN curve stayed the farthest away from the diagonal random line, and its AUC value of 0.99 confirmed its superior performance. In contrast, the ROC curves of random forest, ADA boost, and KNN showed weaker separation. So overall, the result highlight a very big performance gap, while ensemble learning method like XGBoost and gradient boosting perform reasonably well. Deep learning clearly outperform every other approach, both in terms of numerical metrics and ROC curve analysis. The result gives us a few important insights. Firstly, they prove that deep learning models are effective than traditional machine learning model in flood probability, especially when the dataset contains many interdependent and non-linear factors. The CNN deep architecture allowed its capture intricate features integrations, which is why it achieves such a high level of accuracy. Second, when we analyze feature importance like random forest and XGBoost highlighted that deteriorating infrastructure, urbanization, ineffective disaster preparedness, wetland loss, and political factors were the top contributor of flood probability. This is a very important finding. It tells us that flood probability is not only influenced by natural factors like rainfall, but also by human driven issues or poor planning, like poorly maintained infrastructure, rapid and unplanned urban growth, loss of natural wetland, weak disaster preparedness systems. So the model is not just making predictions but also giving us valuable insight into what needs to be fixed at a policy level. To conclude this study provides a comprehensive comparison between machine learning and deep learning models for flood prediction. Our results clearly demonstrate that CNN-based deep learning model outperform all traditional machine learning models with near perfect accuracy, F1 score, and AUC. Its ROC curve also showed that the strongest separation, confirming it as the best performing model. Among ML model, XGBoost was the strongest comparator, followed by gradient boosting, but none of them reached the performance of deep learning. Finally, our study suggested that integrating such deep learning model into flood early warning system could be extremely valuable for saving life and minimizing damage. For future work, more advanced deep learning architecture like RNN or CNN LSTM hybrid could be explored. In short, the project demonstrates how technology, especially deep learning, can play a vital role in building resilient disaster management system for the future. Thank you.